So hello all, I'm Ramana, and today we'll be discussing about in-season forecasting of crop growth using satellite-based features and time series modeling. So why do we do this? Why do we need in-season prediction of crop growth? Farmers have to continuously monitor the crop growth because there are a lot of management decisions to be made. When do you apply fertilizer? How fast do you apply fertilizer? When do you harvest? How much do you harvest? Decisions are such. The earlier you can do this, the better. So the whole idea is in optimizing for time. Early prediction, early intervention. For that we'll be using satellite-based canopy features because we want to automate things, and continuous monitoring by hand is difficult. Therefore we use automated methods. One of the most robust ways to do this is to use satellite-based features, satellite-based canopy features. All right. So yeah, I've already addressed proactive decision making. So we're using PlanetScope API and to download the satellite images, and then we later extract NDVI and GCI canopy features for our analysis. So from the PlanetScope, we are downloading the satellite images at 3 meter by 3 meter resolution at usually roughly daily interval. So we're considering a field in Discol for our analysis. Discol is in Texas. The field has two sections: the top section, the bottom section. And for our analysis, remember we downloaded the images in 3 meter by 3 meter resolution. So we want to convert that into a grid. We do it at 9 meter by 9 meter resolution. So these are just some statistics about when the seeding rate is, when the defoliation rate is, and when the harvest rate is. So as I mentioned, we are using NDVI and GCI for our analysis. While both are correlated highly with the crop yield, we'll be continuing forward with NDVI for now. So modeling the NDVI. What does the NDVI raw data look like? That's the graph on your left, the green one. As you can see, there is pattern, there is a trend, but there is also a lot of noise. The first task is to extract the trend and do away with the noise. Therefore, we do some pre-processing and calibration for our data. The best way to do that is to use a log normal function because this shape matches a lot, and then we adjust the mean and standard deviation to fit to our data. Right, and as you can see, the R-square is around 80% or 75% for this, and this is for 2020 data, and this is for year 2021, and the R-square value is 0.8, which means around 80% fit, and similarly for this. So it's doing pretty well. So what we're going to do next is we're going to consider 2020, 2021, and 2022 as our training data, and we're going to test if our model does well on 2023 data. Alright, so this is the 2023 data we pre-processed. So this is the modeling part. What we want to do here is we want to feed an input sequence to the model and try to predict the rest of the sequence on its own, right? Because we want to do early prediction. We have data till here. We want to see how the trend is going forward. Well, traditionally we can apply simple models such as deep neural networks or convolutional neural networks or whatever it is, and this is even transformer, for example, and it's not doing well. Here it's acting like a mean estimator. Here it's deviating away from the band. Here it's the peaks are not matching. Something's off here. So we can't just throw models right at bay and expect the model to work. We have to address issues step by step. So what do we have? What information do we have? We have something called group statistics, which I call them as group statistics, which are measurements of mean and spread of NDVI band values at the initial stages. Turns out, these things are highly correlated with where the peak appears. So if you can map that with your model, then you have a good reason to expect good predictions. I'm just showing what group statistics mean here. It's the region that's overlapping with the red band. So this is the group I calculate group statistics for this in order to estimate where the peak appears, right? Modeling. So let's do some good modeling here. Let's not just consider simple DNNs. Let's do sequence to sequence. We have an input sequence and we want to predict an output sequence. So the obvious way is to use a sequence-to-sequence LSTM, where you have an encoder, you have a decoder. The way this works is, you have an encoder that converts all of your inputs into a latent state. What's a latent state? It's a hidden understanding of your data. And then you have a decoder, which again tries to map what it understood usually, but you can train it to predict a different sequence based on your training data. That's what I did. This injecting group statistics. Yeah, as I told you, group statistics are important, and we have to inject them in different places. We have different options. We can inject them after the encoder has processed its data, so we can append them to the hidden state, or we can add them as inputs to the first layers of the decoder. We'll see both cases and what works and what doesn't. Right? Let's start with appending to the hidden state. As you can see, there is a significant difference in how the plots are. Which means group statistics works. It's affecting the graph. But what's happening here is, you see this curve here, the red band is not properly overlapping with the green one, which means that it's just weighing down, but it's not helping it predict anything. Why is that? Well, what we did was, you see latent vectors are the model's understanding, and by injecting group statistics to that, we kind of messed up the model's understanding. So basically, the model had understood something, and by injecting group statistics to it, we kind of messed up the prediction here and the model's understanding. So what we can do is, we can try adding it to the decoder as we decided earlier, and we can try. Oh, this thing is up. Sorry, guys. So we can add it to the decoder here, and we can add a softmax layer, and we can try training it. Well, we trained it, and it did well. As you can see, it's predicting well, which means the group statistics injection is working well. But it fails on the test data. As you can see, this is a GIF because during testing you have the data rolling in day after day, right? So you can't have one single image. You have like 100 different images that is stacked, and I've converted it to a GIF. So the red one is the prediction, the blue one is the ground truth. Ground truth data keeps rolling in, and we're doing online fine tuning to account for the new ground truth data as well. So how are we doing online fine tuning? Should we do online fine tuning on the entire model? Probably not. That's expensive. We can train just the softmax layer and fine tune the softmax layer and try and expect some outputs, which is not working in this case. So what should we do? Well, we have a clue. We know that group statistics works. We just want to inject it elsewhere. Where can we inject it? We can inject it into the softmax layer. Here. So we have injected it here now. We removed from the latent state, and then we injected it here. So there are two injections, 1 and 2. This thing is grayed out because during online fine tuning, I'm freezing one of the layers. I'm just fine tuning this part of the network. Alright, what does it look like? So after improvising as such, we are seeing some predictions. I mean, it's aligning well. The red ones are overlapping. You are only able to see a thin band because the lines are interleaving with one another. As long as the red doesn't overflow out of the bonds, it's okay. But there's still a problem. It overflowed here quite a bit. Then, as you can see, as it moves here, there is some peak, right? It goes like that. Why does it go like that? I mean, the graph, you have more data coming in, which means the model should be more accurate with online fine tuning, and the graph should be straight like this. What's happening? Well, you remember, initially we trained our data from, in our training data, we had the input sequence from day 1 to day 65 DAP, and then we predicted the rest. From day 1 to day 65 DAP, you have just this. And if you want to predict this much, there is an uptick here, right? So the model is learning that uptick, and it's enforcing that everywhere across the graph. Now we want to remove that. How do we remove that? What feature can we add? Well, the model needs more context. What is that context? That context is DAP itself. If the model knows how the curve is shaped, and also where during what time the curve is shaped like that, we can try and like rectify for this. Well, that's what I did exactly. I appended in the input sequence of the decoder. In the input to the decoder, I appended the group statistics, and I also appended the DAB for whatever I was predicting for. And I did the same thing for softmax, right? So during training, this thing is accounted for, and during fine tuning, we are tuning both. We are also accounting for this in the softmax, which is going to give us good predictions, and you can see this happening here. You can ignore the tail here because it's irrelevant to us. All we care about is where this peak appears, right? So yeah, let's look at this graph one more time. All the graphs are interleaving. As you can see from its pre-training, it was predicting something else, but as ground data came in, it self-corrected and that peak went down. Let's look at the animation one more time. Right? It predicts something else, but then it self-corrects. Right? This is what we want to see, because now we know that the model has an ability to self-correct, and we want to address this as well. That I can do with mixing up the training data a little bit with different DAPs, and that can be addressed easily. All right. I'm open to questions, and I have 2 more slides, but I'll address the questions first, and then I move on to the slides because they're optional.
So initially, when in the earlier slides, you mentioned that you convert the data from 3 by 3 millimeter to the 9 millimeter grid size, right?
Yeah.
So I was wondering, is there any trade-off of converting that data from 3 to 9, or?
From the difference in information is not that substantial, so you can do a little bit lower test, right? So why do you want to train extra? Any other questions? Go ahead. All right, let's go to the next 2 slides. We want to scale this model up, and this is part of what we did as capstone with Saransh and Funny. The thing I talked about, the satellite image downloading, this is Planet, and we are fetching data here, and this is data management and ML analytics. So we talked about this stack, but we have also implemented this stack, and that. So what's this? This is a data manager network. So in order to integrate different data sources, right? You want a MongoDB database for just querying stuff, and this is a file storage to store images, because images can't be queried like that. So this interacts with your data manager. This is your backend, and that's the front end. You just report it out, and then it's connected to your computer. All right. So we had also built a website out of this. Way in the initial stage, the ML modeling is not included, but you can see what it is. This is the login screen. This is the front end. So we are creating a project here for a farmer or a researcher. I want to forward this slide. We're putting up the crop, the date range. You're choosing a date range. And then this is the map version of it, where you can draw a polygon and mark your region where you want to do the analysis. Then you hit submit. So you're submitting it to our server, all the region and everything. So now the Planet API we are fetching data from the Planet API once we click this. When we say give a date range and we download. So that's the parent date range which you entered earlier. This is a new date range which you just want to do analysis on. When you hit download, it starts downloading. It takes a while. So we pre-downloaded, and then we just retrieved off of it. So we're selecting a date. From the date range you gave, it generates a list of dates you could select. This is the downloaded data from satellite. This is just basic NDVI and stuff. We generated this, and then we are just plotting.
That is all the time that you have, Ramana. Do you have any questions? One question. Okay. Okay, thank you, Ram. Thank you. So our next speaker is Raksha Kharka from University of Maryland, Eastern Shore.
I'd like to present the
Okay, sure. Okay.
Good morning, everybody. I am Raksha Kharka
Yes, sir.
and
The remote is there.
okay,
Yeah.
I don't need that. Good morning again. I am Raksha Kharka, a graduate assistant at University of Maryland Eastern Shore, and today I am very much thrilled and pleased to present our research in modeling synthetic crop yield prediction data using multiple linear regression and neural network regression model. This is a brief outline of my presentation for today. And without further ado, I would like to start my presentation by introducing what is neural network model. So the term neural network itself justifies the definition that it is a type of machine learning model which is inspired by human brains. And like human brain, it has layers of nodes and neurons which process and transform data in order to recognize the patterns and make final predictions and result classifications. And the basic structure or the architecture of neural network model can be divided into three layers. First one is the input layer, where all the data is fed into in the form of text, images, photographs, etc. And the middle layers where all computations takes place using weights and biases, activation functions, etc. in order to recognize the patterns that the data have. And third one is output layer, which is used to make the final prediction and result classification. So neural network model is being increasingly popular in crop yield prediction of agricultural commodities. Unlike traditional statistical methods such as ARIMA, ETS, etc., it has higher ability to learn from complex high-dimensional data and data which have nonlinear nature. But must we know that it sometimes doesn't work well with data with having linear structures and also demand high computational ability to use to make final predictions. Neural network model has both broad spectrum of applications other than just forecasting the agricultural yield, but when it is used in forecasting the yield, it will ultimately help in optimizing agricultural production, supporting food security, informing strategic planning in agriculture, and hence supporting sustainable and productive farming system. Hence, our team aimed to introduce an advanced approach to crop yield prediction by employing a neural network regression model combined with synthetic data augmentation. For our data, we used a completely synthetic data set which we retrieved from Kaggle, which was licensed under MIT. And it contained 20,000 data observations with one dependent variable, which was yield, and 5 predictor variables, which were soil quality, fertilizer, number of sunny days, irrigation, rainfall, etc. We used R version 4.4.2 for Windows software for our data analysis and used the neural network package. And our data preparation involved the visualization through box plot in order to detect any outliers if present and remove them. And also the other statistical measures such as mean and standard deviation in order to measure the center tendency and the data spread. For the neural network modeling, we split the data into train set and test set because from the train set, the model learns from the train set so that it can generalize well in the new test data set. And also we perform the data scaling and normalization to ensure that all the features learn appropriately from the model in order to make the better prediction. This is the model we specified for our 5 predictor variables for one dependent variable. We configured the neural network model into 4 different configurations. First one is the neural network model with single hidden node, and another is neural network model with 3 hidden nodes. Third one was the 2-layer configuration with 3 hidden nodes in first layer and 2 hidden nodes in second layer. And the last one was a 3-layer configuration having 3, 2, and 1 hidden nodes in each layer respectively. And to assess which model or which configurations had high predictive accuracy, we used mean squared error as an evaluation metric. This is the general neural network functionality in our model. First one is the nodes and neurons as input layer, which are the basic units that process the information, and weights and biases, which is used to adjust the parameters in order to reduce errors in forecasting. The activation function, which determines which pathway the neuron, which path the model is directed to. Loss functions, activation function and loss function. And loss function is used to determine how far the actual result is from the predicted result. And the output layer, which where the computation takes place to make the final prediction. And it is just a form of back propagation, which keeps on adjusting weights parameter through weights and biases in order to improve the predictive accuracy of the model. This is just a measure of center tendency and data expect through mean and standard deviation of the data we used. And from the box-plot visualization, we detected around 614 outliers, and the refined dataset consisted of 19,682 data points at a refined dataset. From this ANOVA variance table, we can see that each and every predictor variable has have high significant p-values, which reaffirm their substantial contribution in the model, which suggested that each predictor variable has substantially contributed in defining the yield variation. Also, the F value is very high, which suggested the contribution is of each parameter in the model. And so, for the first configuration, we found out that neural network with a single hidden layer had a high predictive accuracy than other configuration. For 8515 train test data speed, we found out that neural network model with 3 hidden layers had high predictive accuracy than other configuration, different models. Similarly, for 8020 data split, neural network 4 with 3, 2, and 1 nodes in each hidden layer had optimal predictive accuracy. And similarly, for 7525 data split, NN1 was the optimal model or configuration. For 7030, again NN1. And we also compared the predictive accuracy of different configuration neural network model also with the multiple linear regression model. And we found, it was found out that the neural network model with 8515 trained data split had the high predictive accuracy, and we evaluated this using the mean squared error. And from this we can say that model complexity does not necessarily mean that it will perform better than other models. And I would like to conclude my presentation by highlighting that it is very much important to balance the model complexities with the data characteristics in order to have improved accuracy in the model. And it has consistently outperformed the traditional models such as multiple linear regression model, as seen in our result also. And yeah, the future research can focus in other advanced neural network model, and I am also currently working in forecasting the corn yield by hybridizing neural network model with other statistical models such as ARIMA, ETS, TBAS, TDAM, etc. And furthermore, I am very much interested, and I am also starting to work on the using vector autoregression in forecasting the corn and cotton yield together. This is the references I have cited in this presentation. Thank you very much for your patience, and if you have any questions, comments, feedback, suggestions, very much appreciated. Thank you.
Any questions?
My question is last suggestion. Have you tried to use Python implementations? R is fantastic as an employee, but I would suggest move away from R's.
Okay, thank you.
This was good.
Maybe I'll try that in my next study.
You should put that in
Very
your
much.
future work.
Thank you.
I have one question. So trying to understand the rationale behind using the synthetic data set, and are there any plans that you're going to validate
It's
this?
just,
Real data?
yeah, using synthetic data reduces significantly of our time and cost, because the real-time agriculture data to predict the yield from the field data, it is very much cumbersome. So I'm actually very much interested in promoting the neural network model. So I didn't have like real-time yield data, that's why I use the synthetic data.
Okay. Are there any plans to validate with the field data set? Because there might be some publicly available data sets with soil moisture, irrigation, and those kind of things.
Yes, of course.
Okay. Any more questions?
Yeah.
Go ahead.
Just out of curiosity, how many samples do you have?
Sample, it's just a whole data set with 20,000 observations data points. 20,000.
Oh, that's a lot. Okay, thank you.
Because the more data points we have, the
That's it.
accuracy increases and increases. And also the neural network model like doesn't work well with small data sets. that
Exactly.
we have.
That's exactly what happened in my research.
Yeah, it doesn't fit well.
Okay. We still have time, so you will finish slowly. So
Just following
Any
up
more
on
questions?
that, if you're using synthetic data, why 20,000? Why not more?
Because that data set contains only 20,000 data sets, that's why.
maybe there might be a approach that you can utilize this model to generate more synthetic data set and come back and validate with the original data.
Yeah, I'm also planning to, yeah.
Okay. Thank you so much. Thanks. So we do have 3 more minutes until the next presentation. Dr. John suggested me to pass around this QR code. This is for evaluating the conferences so that it helps next year the planning committee to make some suggestions and things like that. So if you guys can fill it up, that would be wonderful. We're going to wait 1 more minute before we invite next speaker. Okay, so our next speaker is Karim Saab, and Karim comes from Texas A&M University. I'm getting the right one, 10:30. Do any of you know Karim? The presentation is here, so Karim will be pleased to share. Okay. So, I don't know, I think we're gonna take a 15 minutes break. Maybe give a couple more minutes, just in case if they show. And we're gonna resume at 10:45. This one? Yeah, maybe what we're gonna do is, you guys would like to see the presentation?
We can discuss,
Yeah.
evaluate.
So, looks like they are trying to do the prediction of pond water restoration. So here is the agenda, you guys can read it. And hopefully they will hear. And motivation, I know a little bit about the motivation. In Texas, we do have a major problem. The Ogallala aquifer declining at a very speedy rate, and we need to develop drought tolerant cropping system, varieties, and things like that. That is what I am expecting that it is happening here too. And a rising cost of irrigation as well, because there are a lot of restrictions to irrigate the amount of water throughout the season. So there are several challenges because of this Ogallala declining in the highlands. So what are the major crops? Cotton, corn, cotton, sorghum. And corn requires a lot of water. That is the reason producers are moving. And this is not from the presentation, my knowledge. So corn needs a lot of water because it is a very thirsty crop. So a lot of producers that we see interact in the highlands in Texas region are moving towards more drought-tolerant crops. For example, cotton, sorghum, and the corn production is going down. So looks like I don't know, need for innovation. Yes, always a need for innovation to save water. So there is no doubt on that one. If you have some similar projects on that one. And looks like they are also working on integrating multiple sensors, soil moisture sensors, remote sensing data sets, and ML modeling to develop some water use efficiency. Most likely hopefully it is in irrigation. So this looks, yeah. Okay, looks like,
I can help.
sure.
Brenda, what is this?
I wonder if,
So what they are testing there is different irrigation treatments. So the 100% ET is that they are replacing, the irrigation rate is to replace the ET daily rate by 100%. Versus you replace 50% of evapotranspiration or crop water use every time they irrigate. And they split the crop area into sections. I guess they have 4 applications, and they have different sensors. Canopy temperature sensors that are infrared thermal sensors, and flow sensor that I have not used that, so I need the author just to explain how those work.
okay. So let's summarize that it is a data collection setup with multiple sensors and multiple irrigation strategies. So this is a flow chart. It starts with UAV and sensor data collection, process the data set, and split the data into training, testing, scaling, normalization, those regular good things that we do. And then hyperparameter tuning and evaluate the model. And once you evaluate the model, try to optimize the parameters and hopefully see if you can make the use of that. I need to check time as well.
You could.
Yeah. So So I think what is water stress? When do we know the plant is really stressed and it needs water? So one biological point is the wilting point. You will physically see the plants wilted, the leaves are wilting, and you can sense that the plant needs water. So what happens if the plants are under water stress? Obviously, first thing, photosynthesis is going to go down because of the chlorophyll, because of the effect in chlorophyll content, and then eventually it's going to reduce the yield, quality, and all those different things. Now, if the plants are suffering, then they're going to have multiple stresses like heat, pest, and all kinds of things. So now, I think, and honestly, if we can predict the water stress, it can help to manage the crop, a lot of things. So I think that is the advantage that they wanted to talk here as well. Looks like they are planning to label, and I think it is based on the image-based water stress detection rather than extracting the features. So, looks like they have vegetation layers as well. If you are new in remote sensing, what we usually work with is you capture the image, you can directly work with the images itself, or you can calculate some vegetation indices. For example, NDVI is very popular, and then try to make sense of what NDVI tells and utilize that. And then they are using the vegetation index layers. I don't know how many yet, but they are classifying, labeling that NDVI layers into different water stress levels because they already had the treatment. So I'm hoping it will help them to label those as well. And then extract those images and train, build the model, and evaluate the model. So looks like they used ArcGIS Pro workflow for image processing. And what you do is you load the UAV image. There are certain processes that you need to follow. For example, image alignment, calibration, and all kinds of things. So, are you Karim?
No.
All right. So, all those steps in UAV image processing, just an advertisement, our program has developed a manual that tells you how to process the UAV images. So you can reach out to Jose if you would like to know more. And then once the image is generated, we call it orthomosaic, then develop the vegetation indices, and then define the field boundaries, and utilize that field boundary to extract the images, individual images from the field. And one more step looks like, I think, okay, FishNet, I am supposing they want to align the images with the orthomosaic. So they are trying to get these plot boundary layers. And then the images are classified into two levels, high stress and low stress. Like we can see the image itself as well. So this is out of my expertise, so if you guys want to jump in.
Convolutional neural network architecture.
CNN.
It has some convolutions in the beginning, it's flattening it out later, and at the end it has a natural neural network. No, that's it. It's just how many layers and what type of layers we put in this unit.
Okay.
And from my experience, this is a baby one, but
Yeah. we start from there, so. Okay, preliminary results, training accuracy, validation accuracy. Thanos, you want to jump in here as well?
yeah. So the blue line tells you about what is the accuracy if you're doing the training. So you're focusing only on the training set, all right? And this tends to go up. Unfortunately, here it doesn't. And then and your loss function should go down. And what we really care about is how does the orange line performs, and that is how the model performs on your validation set, which it hasn't seen before. This is literally like, I've trained the model somehow, and I'm now showing it new stuff, how good or how bad it performs. 50% accuracy, not so great, but it's preliminary results, and they have a baby network. They're on a good path.
Okay. So we're gonna go first. So what are the challenges? Looks like the same challenge in deep learning. AI, the limited data set, a lot of time to label the images, overfitting risk, and things like that. The next step, augment data. I think we talked a little bit about synthetic data sets, and maybe that might be something they're going to come here as well. And leverage multiple features instead of just one feature. And other data sets as well. Looks like they want to integrate the temperature and a SAT flow meter. And then go for multi-sensor feature model. Okay, there is yield prediction model as well. So input data, machine learning model, and then output is the yield prediction. Again, the limitation is there. And I think this is a very nice strategy of integrating crop modeling and machine learning to augment the data set. So the conclusion, the conclusion will be my key takeaways from my experience working in irrigation. Yes, we really need to develop water use efficient systems, either in irrigation or in terms of genotypes, and a lot of areas because of this changing climate, a lot of areas with erratic rainfall and things like that. So, and hopefully AI will help in that area. We'd like to acknowledge all of them. If anyone in the chat or online are from this group, feel free to jump in and say something about this project. So I think we're going to start the next presentation. If you guys have any questions.
Good job to the speakers.
Any questions? We can discuss. I think it is a very good idea as well.
What would be the best way to augment agriculture data which are mostly non-linear?
So there are a couple of models that have been proposed. Generative adversarial network scans or something that does it, especially now with images. There are 2 or 3 implementation. RoboFlow has an implementation. Ultralytics has an implementation for imaging, right? What do you want to do?
For the data, not images.
For the data? Yeah, same thing. The GANs will do that. And there are all techniques as well, right? Like, statistical techniques. But all of them tend to bias your data towards a certain model. No, never say no.
And I think the strategy that they are trying to work might help a lot as well in generating the data set, the regular data set. Because this set, if you validate with really nicely in a couple of fields, then you can simulate whatever, what if scenarios as much as possible and generate a lot of data set to train the model and then come back and validate in the central as well. Any more questions? Yeah, Alex.
Well, it's more than a question. Is I wonder if looking at images that basically with the measuring is basically the photosynthetic machinery presence, but during drought there is a lot of things that happen before that. In fact, when your photosynthetic system gets degraded, that's probably even a little bit too late. So measuring sap flow, as I mentioned, it seems like a second thought almost. That's the real thing. That's where you see early drought stress instead of waiting so long. So maybe the model would be a lot better if you look at that kind of data. So looking at it's not only getting more data, it's getting better data.
Yeah, totally agree on that. And I totally agree on, as soon as we try to capture the response, we might be already late. The farmers panel yesterday said that they saw a symptom in one corner of the field in 24 hours, half of the field was gone. So, but if they had known that that disease was going to come 2 days in advance, then I think they would have saved that half of the field. So anyway, we'd like to go to the next speaker. We are almost there. So our next speaker is Siyu Liu from University of Florida. So The floor is yours.
Okay, hi everyone, my name is Shi Yu, and I'm from University of Florida. I'm a PhD student, and my supervisor is Dr. Yanis Amtidis. And today my topic is optimizing strawberry harvest, planning through machine vision, and AI-enabled predictive analytics. Okay, so why are we doing the strawberry yield prediction? As we all know, like strawberries is very famous. It's almost everyone's favorite fruit. But it's like we only have the strawberries through the winters, and the harvest season really lasts for 16 to 18 weeks. It's like almost 3 to 4 months, and it's harvested almost every week. It's like because it's a weekly product. And also there is so many complicated environments, like we have the environment conditions might change daily, which can impact our strawberries yield, will impact how our strawberries will look like. So, and this can contain like the weather and the pests and disease. All of this can impact the quality. And also, because so far we mainly harvest the strawberries that manually pick up. If you drive past by the fields, maybe in California or in the South or North Florida, you can see like so many workers picking up in the field, which is very labor costed. We all know, like in this kind of conditions, environment, high heat is so tired for us, not good for health. And yeah, so it also costs a high labor cost, and which can add into our price of our strawberries and influence others. And also, also include the farmers. So this cost is something we cannot ignore. And so it makes us might need a accurate weekly prediction, so we can know when will the harvest will peak. So we can organize the harvesting before the best time to pick them up, and like packing to send them to different farmers, deliver to customers. So that's why we are doing this weekly prediction. Okay, so far there's already some traditional yield estimation, but it doesn't seem that enough. First is still needs like people need to count the fruits in the field all by themselves. It's like manually count and manually weighting is still very like labor customized. And also when we counting the fruits or weighting, there is always some human error prone. It's like sometimes you can see the fruit and like some people think this strawberries is ready to be harvested, but other people might not. So they may cause there are some errors happen like during to the manually picking up stuff. And also the traditional yield estimation right now lack of the timeliness. It's like because our strawberries is like weekly harvest. We pick it up this week and next week we pick it up again. So we need something that can predict continuously, like weekly continuously yield prediction. And yeah, so far the traditional yield estimation is not enough for this kind of crops like this strawberry stuff, and also it can cost like high cost and is not that reliable. So to do with all these limitations, we are also because of the development of the machine learning stuff, we are trying to integrate more automatic systems. We using remote sensing and also other different process technologies to develop yield prediction for these specific crops. Okay. Okay, this is towards the smart, towards the wave-specific yield prediction. So here we want to introduce like the object detection models. It's like we take the photos in the field and we use the computer vision stuff like different object detection models to help us to count like how many fruits are here in the field. It's like which fruit is ready to pick it up and which fruit we want to leave it to next week. But this also has some problems because first, the detection models have its error. It cannot have 100% precise. And also sometimes there is some, because like strawberries grows like a small canopy stuff, there is some fruits hidden inside the canopy, which makes us, we cannot capture the, when we capture the photos, we cannot see this hidden fruit. And even our model is good enough, we still cannot detect it, so we cannot count it. And yeah, another one is like right now we need some accurate and repeatable yield forecast, because right now some research develops some distribution map, and or maybe they predict the total yield, but and for the whole season, but not the dynamic per wave outputs. It's like they cannot predict weekly; they might predict like the whole year. So this is very important, I think, to build out a system that can integrate everything together. And even though we have some misdetect or we cannot see some fruit, but with our yield prediction models, we can still help us to predict exactly true numbers in the field. Okay, so here are our research objectives. As I mentioned before, is first we want to develop an automatic yield prediction system. We combine the machinery stuffs and the predictive analytics. And also here, we use multi-source data. We mainly use the weather data, and we use our plant data. It's like the fruit, the flowers, and the immature fruit we count for this week. And we integrate together as input to predict the next week's mature fruit. And yes, so, okay, here is our data collection and labeling. We collect our data from our University of Florida Gulf Coast Research and Education Center, and we collect ability data from December 11th, 2023 to March 4th, 2024. And so far we have 3 varieties. As we can see here, we have Sensation, Brilliance, and Medallion, which is also all very popular among the customers. And we have 4 plots, and for each plot we have 4 plants. And we categorize the strawberry stages into 3 classes. The first is the flowers, and another is the immature fruit, as we can see the small green or white fruit, and also the mature fruit, and which means it is ready to be harvested. And for the weather data, we get it from our Florida Automatic Weather Network. And we have the weather station in our Gulf Coast Research Center. So total, we have 23 features, which might include the strawberry growing. It's like we have the air and soil temperatures, and relative humidity and dew point, and also like winter, fall, wind speed, direction, and the solar radiation, and also this ETO stuff. And there are so many features, so we also try to do the feature selection. We want to figure out, because we cannot put all of these features together into our prediction model, we want to figure out which one do the best, can influence the most to our yield. So we also do the RFT feature selection stuff, and we figure out which one is best, and we use them as input to our model. Yeah, and here we can see we use this IMX477 camera. We capture the RGB images, and we connect it to our Jetson Nano. We integrate it into a small box, so people use the box to take photos in the field. And also we use the LabelMe as the data labeling software, and you can see here we use we generate different kinds of labels we can use as the input to our object detection models. Okay, so this is the workflow of our proposed system. First, we collect the data, and then we label them. And for the model, we use the YOLO V8N model, which is very lightweight, but still accurate and efficiency models. And here we train the models with our strawberry data set from our previous study, and we use this year's data as a test data set. And for the result, we integrated with the weather data to our 2 categories prediction models. First is like the traditional models, and another one is the deep learning machine learning models. And for the traditional time series machine learning models, we tried the RML and VAR, GBM, and random forest, which are both all very famous, I think, classic models. And also for deep learning, we tried the long short-term memory models and this TCM. These two are both also very classic. And finally, we compare it with our manually count flowers and the fruit numbers in the field, and we evaluate our model's performance. Okay, so here's the result from here. We can see we actually get a quite good result. It's like for the flowers, our accuracy can reach 0.69, in mature fruit is 0.76, and for the mature fruit is 0.91. And it is quite obvious because like the mature fruit is red, so it's more easily to be detected. And for the flowers and immature fruit, they might be really small, the size is small, and it might hidden in the leaves, which can increase the complexity when we are doing the detection. And also here from the top tables, we can see that it's like first is our manual count from the field, and second is manual count from the images, and next is our UV detection result. You can see like even we manually counted from the images, there is still a huge gap between the thing we manually count from the field. So it also makes us need to figure out some method to minimize this gap. Okay, and here is our time series model prediction. Is that first we finally find that the MLR achieved the best result doing these sensation and brilliance varieties, and our R-squared score can reach 0.63 and also 0.90, which is really high. But for the genetic, we find that the GPS can reach the highest result. We separate these three varieties because we think the factors that influence their yield might be different. And you can see these waves is like it's predict exactly with the yield for these three varieties, which is quite precise. Okay, and also here is our neural network prediction, and we find that LSTM is better than the TCM, but in general the result is not as good as the traditional time series yield prediction stuff. So it can due to a lot of reasons. For example, our dataset is not big enough, and in my case, it cannot really fit in the huge neural network models. And probably the factors between the weather features and the result they are just linear. So we still have to figure out. Okay, here is our conclusion. It's like generally sometimes a single model might have a better result, and we use this mainly to reduce the labor and organize the harvesting project. So yeah, I think that's all. Any questions? Yeah.
So on your methodology, you mentioned that you use the NVIDIA Jetson Nano.
Yes.
How did you deal with the power requirement of using it outside in the field?
Oh, it's like we have a built-in battery which can supply it, but like because we just hold the box and take the images, and it's actually quite fast. So for our battery, it can last for an hour, and it's completely enough. Yeah.
For every target area, there's only one image, or are you taking it from multiple sides?
Yes, so far for this version, we only take the images from the top side, but for this year's plan, because it's next year, this year we plan to have the top view and also two side view. Yeah, so we want to see more, so make it more precise. Yeah, anything else?
Thank you.
Thank you. Thank
So our next speaker is Mohammad Rahman from Tennessee Tech University.
Good morning, I am Mohammad Bayatun. Thank you for being here. And today I'm going to present our research on AI-powered hyperspectral imaging for solving quality estimation. The aim of this research is to improve the real-time solving quality assessment using advanced imaging and machine learning techniques. So solving is one of the most important economic crop, and for that reason, US has produced 3.47 billion bushel of soybean in 2024 alone. After harvesting, the important thing to consider is you need to find out the break of the splitted soybeans and also the impurities. Because if you have a high amount of impurities and broken soybeans, then the quality of the market and the market value and the quality of the soybean would be degraded. And usually we use the manual inspection of the harvested soybean quality estimation. So we propose a machine vision based technology for this automated soybean quality estimation. So from this image, I think you can get a clear idea about what actually we are working on. So if you can see, there are 4 types of objects available when we gather the harvested soybean. So one is the disease soybean, which is affected by some fungus, and these are the normal soybeans which we are expecting to have after the harvesting. And these are the broken and split soybeans, like the soybeans are broken during harvesting. And these are the stems and pods and other materials. Mostly they are non-soybean objects. And if you see more closely, like even in the naked eye, it is difficult to differentiate the normal soybean and the split soybean when the split soybean is in this orientation. So that's why we actually want to integrate some advanced imaging technology to solve the issue. Some researchers have already been working on that, like Momin and others. They have applied 2 different light sources, front light and backlight. And using backlight, they actually solved the issue of differentiating the normal soybean and split soybean. And another research work has been done by Kimmer and others. They actually used different morphological features of the soybean, like soybean length, soybean width, projected area. This type of morphological features have been used for classification of soybean traits. And they actually did not differentiate the normal soybean and split soybean. So after studying these research studies, we actually came to the conclusion, we actually find out a research gap, like can we do the classification of this harvested soybean under a single light source instead of front light and back light. So we set our objective to develop a non-destructive method for soybean classification using the image or the spatial feature information. So for our experiment, we prepared our data set. In our data set, we actually collected over 3,050 objects of soybean and other objects. And this table actually gives you the quantitative information about our training data and testing data. And in our experiment, the training data set and test data set both are totally different and totally separated. And we have also employed this hyperspectral imaging device for our analysis. And we actually captured images from 379 nanometer to 1020 nanometer. In this bandwidth, we actually captured images in 300 different frequencies. So for each sample, we actually have 300 different values for 300 different frequencies using the hyperspectral imaging device. So after applying the hyperspectral imaging device over the soybean sample, we get this type of reflectance. And if you can see, like there is a difference between the disease soybean and the normal soybean. And actually, if you consider this region, like for the disease soybean, the spectrum is more broad than the normal soybean. So yeah, we can differentiate using this spectrum between the disease soybean and the normal soybean. And if you consider the normal soybean versus the other objects, yeah, the spectrum shape is totally different. So yeah, we can differentiate the normal soybean versus the other objects. And actually, the challenging part was the normal soybean versus the split soybean. And we have considered two orientation, in this orientation and this orientation. So overall, the normal soybean and the split soybean, their spectrum shape is pretty much similar. But if you look more closely, then you can find out that the normal soybean actually bit brighter under the light of the hyperspectral imaging device, and we actually use the normal white LED. And split or broken soybean, it looked bit dimmer. And if you look into the y-axis, the reflectance value of this normal soybean and split soybean, you can see the normal soybean ranges from 0 to 20,000, whereas the split soybean is ranges from 0 to 15,000. So that actually motivated us, like since their reflectance value bandwidth is different, and also the shape of reflectance is also different, so we can use these values for the machine learning model. And since we have the 300 values for hyperspectral imaging because of the 300 different frequencies, so the more input and the more data we provide to the machine learning model, we expect to have more accuracy. That was our intuition for this approach. So here is the overall methodology of our classification model. So we first collect the data, and after collecting the data, we do some pre-processing. For the pre-processing, first we apply the filtering, and after filtering, we actually remove the noise. Then we apply the intensity thresholding. Using the intensity thresholding, we actually remove the background of the images. Then we apply the watershed algorithm for boundary tracing, and we followed by some morphological operations like opening and dilation, so that we can separate the objects and create a mask. And after creating the mask, we actually apply that mask to the soybean images, the hyperspectral image, and then we actually extract the reflectance of each object. And for each object, we actually extract only one value, only one mean value of the overall spectrum for the single object. Then after collecting the mean value for 300 frequency for each object, we put those data into our Excel file to prepare the data set. And after preparing the data set is a tabular data set, and we have observed that in case of tabular data set, some ensemble models, especially the CAD-boost classifier, they perform very good in terms of the tabular data set. There was a research done by other researcher, and so we construct the ensemble model, then we run the model, and run the classifier using the training data and build the model. And after building the model, we apply the test data and evaluate the performance of the test data using some performance matrices. So from the performance matrix, we got that the ensemble models like random forest, CAD-boost classifier, they perform better than the traditional classifiers like the naive Bayes, decision tree, KNN, and we are actually surprised with the accuracy. Like the accuracy is more than 99% because we have actually 2200 of training data, and for each training data we have 300 feature values for 300 different frequencies. So we have provided a lot of information that is actually reasonable for having this sort of accuracy. And the area under curve is also 0.99, which is very much significant. And here the confusion matrix for the training data set and testing data set. And in the training data set, only 4 samples were misclassified, and in case of the testing data set, only 3 samples were misclassified. So yeah, the performance is very good under the CAD-boost classifier. And here is the ROC curve. Since the accuracy is very high, so the ROC curve is almost 1, like 99 point something. So yeah, out of 800 samples, 3 or 4 misclassifications. So it's very close to 1. And these are the other statistical performance matrices. And in all the statistical performance matrices, for like precision, recall, F1 score, and kappa value, the CAD-boost classifier performance was more dominant than the other classifiers. So in conclusion, we can say that though the normal soybean and split soybean look very much similar in terms of the color, texture, shape, but their the reflectance value, or you can say the spectral information, is different. That is why we can actually use the hyperspectral imaging for differentiating the normal beans and split soybeans. And we have only considered the mean value because mean value can capture the overall bandwidth of the individual object. We have also tried with all the pixel value, and in that case the dataset was very high, very huge, but we still tried in our experiment. But in that case the performance is very good. So only mean value actually worked very well. And yeah, we have found out that for our tabular dataset, ensemble models like random forest can boost it, even we have tried the XGBoost classifier, so they perform very well against the other traditional classifiers. In future, we have a plan to incorporate the texture informations from the images because we have only considered the spectral or the frequency information, but later we have a plan to integrate the texture information. And we have also planned to apply different deep learning model architectures, and we'll compare the performance based on those model architecture response. So, thank you. This is all I have.
Any questions? Do you have time?
Do you consider the feature selection?
In case of our feature, since we only use the spectral information, we only consider 300 different frequency for our features. Our frequency spectrum started from 379 nanometer and it ended at 1020 nanometer. We didn't consider any other texture features like brightness, contrast, then GLC. These are features are not considered, but yeah, we have planned to do that in our next phase because we have considered to incorporate the texture information in our dataset.
Do you think that the accuracy obtained because of the model overfitting?
Seems like that it is overfitting, but the model gives this result. So actually, we did some careful port validation. That's why I believe that accuracy is that much high, and also the misclassification rate is very negligible. And so you can see like the value, the normal bins and the split bins, the range is like this is from 0 to 20K and these are from 0 to 15K. So actually, since the value is different by a significant margin, so that is the intuition for having a better result and better classification accuracy.
Any more questions? Go ahead.
I want to ask about the cost and efficiency of this method. Like, can you imagine using this in an actual harvest signal?
Cost and efficiency. Hyperspectral imaging we have in our lab. It's a bit costly, but you see, like Mr. Momin, they also applied these techniques for. They also applied their technique for differentiating the normal bins and split bins. They used two light sources, and instead of two light sources, we actually use one single light sources. And they have a problem with the backlight because in the backlight they use a glass plate, and under the glass plate they use the light. And normally when they put the soybeans, after a certain time there is some sand, some grains, so you need to clean the glass plates. So we have no problem about that. So in terms of the efficiency, we can say single light source would be more efficient than double light source.
Okay, thank you.
Since you're doing mean estimation area of pixels, why do you need high-risk cameras? You could have taken slightly low-risk cameras as well, right?
Okay, so actually it's not about the resolution, it's about the taking values. In case of RGB image, you can have three values, like the red channel, green channel, and blue channel. And in those three channels, you can have three frequencies. For red channel, we use normally, for blue channel, we use 460 nanometer. For green channel, we use 549 nanometer. And for red channel, we use 640 nanometer. So only three frequency value. So only three value. It doesn't matter what type of resolution you're taking. We're actually taking hyperspectral because we are taking images in 300 frequency. So whereas instead of 3, we are taking 300. So a huge amount of value, and we actually comparing those values.
Okay. Thank you so much.
Thank you.
Okay, so I am the next presenter, and my name is Mahendra Bandari. I work as assistant professor at Texas A&M University. So today I'm going to present about some of the work that we did in Armenia to develop a winter wheat yield prediction framework, and it is part of a bigger project, which is developing the AgroTwin system that I'm going to talk a little bit later. And as you can see, a collaborative effort. So many institutions are involved, and the project was funded by USAID, but recent changes, we are no longer continuing this project, but trying to find some money to make sure we develop something out of this project. Okay, and one more thing, the original presenter was supposed to be Lei Zhao. He is a PhD student in computer science, so I got his presentation and modified as an agronomic version. So you're going to hear more on the conceptual and the framework ideas that we have been working on. So a little bit about Armenia. It is the country in Asia, but it is neighboring to Europe, nearest neighbor Turkey, and on the other side Iran. And why this project in Armenia right now? So Armenia and Azerbaijan were in war for a few years, and they lost a lot of cultivated land, and they would like to see what is the future world. And they want to focus on wheat because wheat is the major crop, and because of the war, the yield are declining, so they want to see how they can revive that industry. And the country is divided into 10 provinces, and the wheat is mostly grown on that. I don't know if it works, but anyway, in the Shirak region, that province is one of the most popular region for wheat production. And then what we did for our study is we selected 3 mega environments so that we capture the environmental variability to train the models and validate some of the algorithms. And within those 3 mega environments, we selected 10 producers' fields, and these fields range from half acre to all the way to 20 acres as well. So we do have that scale in terms of looking into small fields versus a little bit larger fields. And the agronomic table. So you can see the mega environments all the way to the right, 3 different mega environments. But one particular thing here is that Maralik, which is one of the mega environment, which is planted a little bit early versus the other parts in the environment. And then you can see the range of yield that we see ranging from 1 tons per hectare to 7.6 tons per hectare. So 1 hectare is 2.47 acres, so it's almost double. So we do have that range in our data set across these 10 different locations. So the idea of AgroTwin system, and we can redefine this twin system in so many different ways based on what we really want to achieve with this digital version of what we see. So now for this project, the AgroTwin represents the entire agricultural production system as a mapping tool. Now we started with developing one algorithm trying to see if we can locate all the wheat production fields across the country. A poster was presented in this conference, and we are trying to publish that. So I'm not going to talk about that. And another component that we have is we would like to see how we can utilize this UAV and satellite systems to develop the digital twin of crop growth and development. Dr. Landivar is here. He presented a little bit yesterday, and that the concept of representing the digital version of crop growth and development. And then how we can utilize all of that to make in-season forecasting. So now, what the entire framework, if we look at the picture, is that it can be used for policy making, as well as for the producers to make some decisions as well. Now, going to this digital version of plant growth and development. So, this is a very good graph to tell the story, because the response, the crops growth and development show the response of, for example, nitrogen uptake. If we apply the nitrogen, the response is there in the crop. And how we can capture that response in terms of growth and development is what we define as the digital twin, the green line over there. And what made it possible is that we can collect a lot of data set using UAV and satellite systems very, very efficiently. And from that, we can collect so much of information that tentatively represents the digital version of plant growth and development, which means, for example, those first 3 features, they are mostly on the structural properties. We want to know what is the size of the plants and those kind of things. And rest of these are mostly on color, photosynthetic efficiency, chlorophyll content, and so many different things. So an indirect approach to try to understand the response as well as the plant itself. So how the data looks like. We started, the team over here started collecting data end of March. This is the first time they started with UAV, but did a very good job. The data looks very nice to work with. And what we do, collect the images, process, and develop those features that I mentioned earlier. And this is one of the fields. And I'm going to talk about this field throughout this presentation because we visited that field by ourselves, and we think that was a very, very good field, nicely managed, and one of the high-yielding fields as well. So now the problem comes. When we try to develop the yield prediction, we heard a little bit about synthetic data, but the challenge is there, especially the developing countries, is they don't have the machinery to do the yield mapping. There is no John Deere yield monitor system. You cannot really spatially distribute the yield data. But the team was able to collect some samples from 4 fields, and you cannot really go all the way through the field because you're going to damage the crop. The producers will not like it. So you need to be always careful. So the yield data is limited in the developing world. And what we have, another number, is the number that producer gave for us, that how much yield they harvested from that particular field. So that is the most ground truth that we can depend on. And the sampling never represents the population, as you can see in that picture. In the field 8, there is a huge gap between the farmer's number versus what the samples told us. And then I am confident looking at that field that sample really didn't represent that field. So, but we try to see how we can utilize the farmer's number in there. And then let's try to see what those features, the canopy features that I described, do they really correlate with the yield? And the graphs are not so pleasant to see, but at one point of time, you can see there is some stable correlation, especially with this excess grain index. You can see in multiple fields the correlation is there. But, you know, it is not that good either as well. So, now the yield prediction protocol that we have been focusing on is that the data is collected, features are extracted. So one of the major things that we need to do always is that the time series data set, the time steps are never going to be consistent because you'll never be able to collect the data exactly at the same time in multiple locations, multiple years. So best way, try to translate that, interpolate it, and try to develop a continuous time series data set. We try to use the log normal, polynomial functions, or logistic functions, depending on the variables. And once it is continuous, then we try to train the models. And I'm going to talk a little bit more about that later. So we went, and even with those little data sets, almost 200 data points, we still said, why don't we try the algorithms that really don't need that much amount of data and see how they do. So field 3, field 5, field 9, 3 fields were used to train the model. And then one of the field was used for testing. But MLP was looking good. But I still, think that this data is not really enough for us to do the generalized yield prediction across the region, because our target, if the project was going to go for next 5 years, was to continue for entire country. So, and then the thought came that why don't we try to see what we can find in the US and then try to see if it works in Armenia, so that it could open up a lot of doors for developing countries who really struggle with the data collection. And we luckily found one of the wheat farm located in Amarillo, which is 150 acres. And then the ill monitor data, you can see the spatial distribution. Now, from those 30 points, we can go as many data points as we would like to. And one thing to note is that one of the mega environments resembles the planting date almost in Amarillo as well. So the planting, the season is comparative too. Unfortunately, we didn't collect the UAV data in that location, so we need to find another alternative. So we decided, why don't we check with the PlanetScope satellite image. And good things, I have been working on this for past couple of years now. I really like this platform because it has a daily coverage, global coverage, and then high resolution. And then what we do is we try to minimize a lot of errors, so trying to get the 9 meter by 9 meter grids, extract the data sets, and then I'm going to present this to Phil as well. And now from those 30 points, now we have 6,800 points to play around. So this gives the confidence that we are looking in the ill prediction model. So let's see how and then we derived so many different indices, but NDVI seems to be very popular, so I'm going to talk about that. And if you look at this plot, we managed to capture cloud-free images 60 times from January 1 to the end of June in Amarillo. So that is a lot of time series data set. You can do a lot of things from there. And then 30 times in Armenia, still it is representing the entire growing season. And it represents very well. Now in both the environments, what is the regular growth habit of the plants? Starting very slow because it is very cold, and then at one point of time, as the temperature rises, the growth starts to pick. So we can see that resemblance in the growth habit in both the locations. And then as soon as it peaks, it starts to silence because wheat is annual crop. Now major difference is when that peak happens. The peak in Amarillo happens almost a month early than the peak in Armenia. So now that is one of the things that I'm going to talk in the next slide on how to deal with. And another thing is the season is a little bit longer in Armenia compared to Amarillo. But still, we said, let's try to see if we can align those curves. So one theory is that instead of picking the 1st of January as our first day, why don't we pick the day when the growth really started to happen in both the locations? And as you can see, the growth really happened very early in Amarillo, the blue line, versus the orange line in Armenia, almost 30 days. So why don't we use that 30 days and bring it back together? Now both the curves are aligning very well with each other. So now only difference is the magnitude. And then the data interpolation techniques go through. It looks a little bit unpleasant, but still getting there. And then the correlation, the relationship looks very good between the NDVI and the yield as well. And then we train the model using this 70-30 for Amarillo. And then the graph is, the scatter plot is looking okay. So we decided, why don't we test it in Armenia? So now our ground truth is 7.6 tons per hectare. And our model was able to predict 6.9 tons per hectare, even with a little bit of enhancement that we can do. And Ramana presented that framework over here. So the digital twin, how it is going to work together is you collect the data set using the satellite, extract the features, go through that forecasting mechanism, So you are able to forecast NDVI every day for the rest of the season, starting from 65 days after planting. That goes to the yield forecasting model, so it continues the loop throughout the season. With that, thank you so much. I'll take any questions. I can take one question if you have.